Recent data have revealed that 3I Atlas is behaving far more strangely than scientists expected. According to Professor Avi Loeb, the object is losing mass at a rate no known cometary model can explain, hinting at either an extreme fragmentation event or an unknown physical process at work. The numbers alone are staggering. In late October, just before perihelion light curve measurements revealed a sharp and sustained increase in brightness, nearly 3.6 magnitudes in under 48 hours. For a comet barely 1 to 2 kilometers wide, that's equivalent to an entire mountain vaporizing in a day. Loeb's updated calculations from Harvard indicate that during its closest solar passage, the object released more than 2 million kilograms of material every second, an expulsion so violent that under normal physics, it should have disintegrated completely. Yet telemetry shows a coherent body still producing highly collimated jets. We are watching an energy budget that doesn't close, one researcher summarized. To match the mass loss rates the nucleus would need to span at least 14 kilometers, perhaps 20, assuming primarily carbon dioxide sublimation. But Hubble imaging pinned the diameter below 2 kilometers with no evidence of any hidden mass reservoirs. You can't hide that much surface area from Hubble's optics. Something in the equations refuses to balance. This next observation shouldn't exist if the object behaves like a comet. Spectral readings show that instead of reddening under solar heating, like every other dusty, ice-rich nucleus ever catalogued, 3I Atlas turned sharply blue. Its reflectance shifted toward shorter wavelengths as it neared the Sun, implying surfaces rich in metallic compounds or exotic silicates polished clean of dust. Think of a snowball that becomes glossier and more reflective the closer it drifts toward a furnace. That's not standard thermodynamics. Normally, heating creates dust plumes that scatter light, producing the familiar yellow-white hue. Here, the opposite happened. Increased energy yielded greater reflectivity and spectral hardening. By late October, sublimation rates had risen from a few hundred kilograms per second to nearly 2 million, a 6,000-fold jump. To sustain that output from ice alone would require more sunlight than the Sun provides at that distance. The mathematics is precise. Solar radiation at perihelion delivered roughly 700 joules per square meter each second. Yet to vaporize that much carbon dioxide or water ice, the total absorbing surface would need to span over 600 square miles, equivalent to a spherical body at least 14 kilometers across. The nucleus we actually see is 1/8 that size. So either 3I Atlas fragmented into millions of smaller pieces, each exposing its own surface area to sunlight, or something else is driving the acceleration. Imagery from early November appeared to support the fragmentation model. Several observatories reported the main body developing elongated jets and an anti-tail extending nearly 1 million kilometers toward the Sunan orientation that violates ordinary solar wind dynamics. Under standard conditions, dust and gas stream away from the Sun, not toward it. But here the geometry reversed, suggesting either complex magnetic interactions or directed ejection. The opposing tail stretched 2.8 million kilometers outward, nearly twice the Earth-Sun distance when projected on the sky. Additional analysis revealed at least 7 narrow jets maintaining consistent angular separation over several nights. Random debris fields don't organize themselves that way. If 3I Atlas had simply exploded, we should see a diffuse chaotic cloud expanding outward. Instead, we're seeing order structure patterns of emission too clean for thermal breakup. Loeb's team calculated that to maintain the observed momentum, flux nearly 50 billion tons of mass expelled each month. The object would need to possess either multiple intact nuclei or a distributed system of fragments somehow acting in concert. The physics doesn't reconcile easily. Either nature is doing something no model predicts, or the mechanism is controlled. Now comes the unsettling part. Trajectory measurements collected after perihelion show the object accelerating faster than gravity and outgassing alone can account for. The deviation is measurable roughly 94 kilometers per day, squared at closest approach, even as solar radiation pressure decreased. In simple terms, it's speeding up while moving away from its energy source. That shouldn't happen. When the Atlas Survey telescope in Chile first detected the visitor on July 1, 2025, it appeared unremarkable. Oumuamua displayed non-gravitational acceleration, but no visible outgassing. Borisov behaved like a textbook comet. 3I Atlas now straddles the line between them, combining the compositional signs of a comet with the kinematics of a craft. By mid-August, Webb's infrared spectrometers detected a carbon dioxide envelope nearly 350,000 kilometers wide, yet the molecular ratios within that gas iron nickel magnesium didn't match any catalogued solar system comet. They looked skewed, as though sampled from material forged under a different stellar chemistry. Even the isotopic ratios of carbon and oxygen hinted at origin conditions inconsistent with our Sun's protoplanetary disk. This is a rock that formed around another star. Still, all of that could fit within natural variation until the jets appeared. The British Astronomical Association's Michael Butner and astrophotographer Frank Nebling captured images on November 9th that forced a rethink. Against all expectation, the jets weren't chaotic. They were symmetrical, narrow and steady, pointing in precise repeating directions, night after night. Photometry confirmed collimation angles separated by exact multiples of 18 degrees numbers, too tidy for thermal chance. The conclusion feels uncomfortable, yet the data is stubborn. Either millions of fragments are releasing gas in synchronized bursts, or there is some underlying order guiding the emission. Loeb is careful not to speculate beyond the math. What Loeb means by engineered propulsion is simple in physics terms. Sublimation can produce reaction thrust, but its exhaust velocity is low meters per second, not kilometers. To produce the measured acceleration, an active system would need exhaust speeds orders of magnitude higher with vector control to maintain direction. In principle, that's exactly what directional thruster arrays would do. Their exhaust patterns would appear as narrow geometric jets, just like those photographed in November. It's an extraordinary suggestion, but Loeb's discipline lies in refusing to treat extraordinary as impossible. He doesn't claim proof of artificiality, only that the data allow no easy natural explanation. Fragmentation remains viable, but the fragments themselves behave too coherently. Upcoming telescope campaigns will decide. Hubble's November spectroscopy will measure the thermal signature of each jet. Webb's December imaging will test whether the nucleus has indeed split into millions of grains, or whether distinct objects are maneuvering in correlated ways. If the spectral lines show only scattered dust and ice, the case closes as a dramatic but natural disintegration. If they reveal consistent temperature regulation or emission spectra incompatible with ice, the conversation changes entirely. Either way, the clock is running, because 3I Atlas is already moving outward from the Sun at over 150,000 miles per hour each day. The signal weakens, the window narrows. By December 19, 2025, it will make its closest approach to Earth still bright enough for our best telescopes to capture. After that, it recedes into the dark past Jupiter by spring, and then beyond the reach of any instrument humanity possesses. Every measurement taken in these weeks will define what we know forever. At this point, All that's certain is that the object violated multiple expectations: energy balance, color change, jet geometry, and trajectory. Each by itself could be explained away. Together, they form a pattern that resists ordinary classification. If the anomaly holds, 3i Atlas will stand as the most consequential interstellar discovery since humanity first detected extrasolar planets. The discrepancy widened after November when new observations revealed secondary outflows that brightened and dimmed in synchronized intervals, roughly every 7.3 hours. Periodic variation that's stable often points to rotation, but rotation alone cannot account for symmetrical jets maintaining fixed spatial alignment across multiple rotations. The implication is that each emission event is not a random plume, but a timed release. And that raises an unavoidable question: what mechanism can regulate timing across dozens or even millions of fragments traveling through interplanetary space? Analysts at the European Space Agency's Near-Earth Object Coordination Center modeled several natural possibilities: rotational modulation, cryovolcanic pulses, gravitational torques among fragments. None matched the periodic stability observed. Each natural model predicted jitter and random phase drift. The data didn't drift. It repeated with clock-like precision. Meanwhile, ground-based spectra from Chile's Cerro Paranal Observatory confirmed ultraviolet emission lines inconsistent with typical volatile compounds. Loeb's latest paper draft, now circulating among peer reviewers, outlines 3 scenarios. The first, a catastrophic breakup where millions of icy fragments continue sublimating in parallel. The second, an unknown natural mechanism producing directed mass ejection at unusually high exhaust velocity. The third, the one no one wants to say aloud, the controlled propulsion hypothesis. In all 3, the core mystery remains the same: the energy source doesn't balance. It's difficult not to sense the weight of that moment. And yet, perhaps the most haunting aspect isn't the data itself, but the timing. The probability that a body ejected from another star system billions of years ago would intersect our solar system precisely when Earth possesses technology capable of resolving it is almost incalculable. Statistically, the alignment feels deliberate, though science resists that word. It's a reminder that the cosmos doesn't owe us coincidence or explanation. If 3i Atlas truly fragmented, those fragments are now spreading along divergent orbits, each glinting faintly under sunlight as they recede. Every data set feeds into one question: what is driving the acceleration? Solar radiation pressure is too weak. Outgassing can't sustain it. Magnetic interactions lack sufficient field strength at those distances. Nothing in conventional physics closes the equation cleanly. Whatever the answer, it will alter models of how matter behaves when expelled from other stars. As December begins, the countdown tightens. In barely 2 weeks, 3i Atlas reaches its closest Earth approach, offering a final fleeting opportunity for direct observation before distance swallows it. After that, the next chance to witness an interstellar visitor may not come for decades or longer. The observations made now in these nights will stand forever as the complete record of a mystery that might have touched our solar system only once. The telescopes are still locked on. The data streams are still coming. For a few more nights, humanity watches, waiting for the final numbers that might tell us whether the impossible was simply misunderstood, or whether something from the interstellar dark just brushed against the edge of our understanding and kept going.